All right, good morning, everybody. So today we're going to finish up our review. Our final exam, I believe, is scheduled for Wednesday morning, 8 a.m., bright and early. Come with your model kits, several pencils. Wouldn't hurt to have a little pencil sharpener. And a nice eraser. Do not bring just the eraser on the end of your pencil. They don't erase well, and you might go through the whole thing. You never know. So bring a good eraser. And relax. You got 2.5 hours to take an exam that should only take you about an hour and 45 minutes. So there's plenty of time to get through the material. And you will have a scratch piece of paper, and you will have what's called a data sheet, which will give you a few abbreviations, a partial periodic table, and all that kind of stuff. So you'll be in good shape. So today we're going to talk about stuff that's more in line with the end of 255 and into the 256 kind of stuff. So we're going to be thinking about things like nucleophilic substitution, elimination, electrophilic addition, carbonyl compounds. One thing you should know at this point, right, is carbonyls are very, very useful in organic chemistry. We can do all kinds of stuff with carbonyls. And then we'll talk a little bit about synthesis and analysis. If you only have time to review a few things, I would strongly suggest that in the ACS Study Guide, you focus on these one-pagers. Okay? I'm not saying all you need to do is study these one-pagers. I'm just saying it's in your benefit to study these one-pagers, because these one-pagers really summarize quite nicely the stuff that you need to know. Okay? So here you've got nucleophilic substitutions and eliminations. And by the way, if you don't have a copy of the ACS Study Guide, you can, after class, go buy one in the chemistry office, or you can go borrow the one that's on reserve in the library and copy what you want. Okay? So nucleophilic substitutions, what types of nucleophilic substitutions did we learn about? SN1 and SN2. You're going to need to know what the stereochemical outcomes of those different reactions are. You're going to need to know the kinetics of those different reactions. You're going to need to know what the reaction diagrams look like. How many transition states do we have in an SN2 reaction? 1. How many do we have in an SN1? 2, right? How many humps do we have, right? That's what we're talking about. And in between those two mountains is the intermediate. What's the intermediate in an SN1? Carbocation, right. So this really summarizes that all up nicely for you. So again, these are very, very useful things to start your studying for the final exam. Let's get into working some problems. In S1, the reaction of benzyl bromide with azide ion is shown in the box. When the benzyl bromide concentration is constant and the azide concentration doubles, the reaction rate is observed to increase by a factor of 2. When the azide concentration is held constant, the benzyl bromide concentration is doubled, the rate of the reaction doubles. What is the correct rate law for this reaction? It is D. It's an SN2 reaction, right? I've got a good leaving group. It's on a primary carbon that's benzylic. I've got a very good nucleophile. That's going to have to be an SN2 reaction. And the data tells me that if I double this, the rate doubles, and if I double this, the rate doubles. This is the only one that fits that information, right? But if you're also looking at this, you can really almost eliminate everything else. Where have we talked about in organic chemistry where we have rates that are squared and or whatever 4 is, right? We haven't. You could have looked at that and really eliminated things down to D here. In S3, what is the structure of the reactant that would yield the two products shown? Eliminate one for me, please. A. And why can we eliminate A? Yeah, there's no leaving group on there, right? What other two can you actually eliminate as well? You can eliminate B and you can eliminate D. That's right. C is the correct answer, right? Why can we eliminate B and D? Okay. That's not a bad thought. But if I was to try to add alcohol across this carbon-carbon double bond, will alcohol alone do that? I need a catalyst, right? I need an acid catalyst, of which I don't have. This one I have a leaving group. What kind of reaction is this, SN1 or SN2? It is SN1. This leaves, you end up with a carbocation here that is stabilized by resonance. The lone pairs on oxygen can donate to it, right? And so you can get alcohol substitution, right? But remember, SN1 is almost always accompanied by elimination as well. And so that's why that is a good indication that that's going to be an SN2, or excuse me, an SN1 reaction. Which alkyl halide would you expect to undergo SN1 hydrolysis most rapidly? That's right. What do we know about SN1? We go through a carbocation intermediate, right? And so we know that tertiary carbocations are more stable than secondary, more stable than primary. But that doesn't answer that part of the question, right? Because they're all going to give me tertiary carbocations. So what is this question really asking you? Which one is the best leaving group? And what do we know about the leaving group trend? Increases as we go down. Very good. So the iodine or the iodide molecule A will obviously be the quickest. This is exactly that demonstration that we did in class that you all videoed, right? Except we did chloride and bromide. We didn't do iodide. And I told you why we didn't do iodide, because the reaction would be over so quick, it would just turn pink as you add the solution, okay? What is the major product from the elimination reaction shown here? First and foremost, you need to ask yourself, what kind of elimination is this going to be, E1 or E2? E1 is favored by what? Tertiary alkyl halides, which here we have a secondary. Polar protic solvent. And does the base have to be strong? No. How about E2? Need a strong base. Do I have that? Well, it's reasonably strong. They're also favored by good leaving groups. But polar aprotic typically favors them, right? But this is a secondary alkyl halide. Is the leaving group good? It's pretty good. Chances are this is going to be an E2 elimination, right? So given that, what's the answer? Why are you wrong? What are you forgetting in an E2 elimination? How does the leaving group and the hydrogen have to be arranged? Antiperiplanar, right? Or trans, if you want to think of it that way. No matter how I ring flip this, can I ever get this hydrogen and that to be antiperiplanar to one another? I cannot. But when I ring flip this, what you'll find is that the bromide and this hydrogen are antiperiplanar to one another. And so you will eliminate here to give a carbon-carbon double bond, and the deuterium will remain. Okay? So don't forget that. You have, I mean, just because you're given a ring, you have to remember that these rings are flexible. They can a ring flip. Okay, unless they tell you as shown or something like that, you have to assume that you can ring flip these. This would be a perfect example of where having a model kit will help you, right? And so I strongly suggest that you have at least one 6-membered ring already built so you don't have to waste time popping together all the parts. What is the major product of this reaction? Whose rule should we be focusing on here? Zaitsev's rule, right? So if we're focusing on Zaitsev's rule, which two would you eliminate? I'd eliminate A. And we can eliminate D for a different reason, right? Why can we eliminate D? Yeah, the bromine's not anywhere close to that, right? So we can eliminate A and D. You just went from a quarter to a half in terms of your odds, right? Every good gambler puts their money on the table at 50-50 odds. ABCD. So we've got B or D, or excuse me, B or C. Which one's the correct answer? Why B over C? They're both tri-substituted alkenes. Ah, very good. Yeah, so this double bond is now conjugated into the ring, which adds stability. This one is not. So they're both tri-substituted, but this one's going to be more stable due to resonance conjugation. It actually turns out that these hydrogens are actually more acidic because they're on the benzylic carbon than these hydrogens. Okay, and so, but your explanation is exactly why. Why is what?
It's resonance and the hydrogens are acidic.
Yeah, so the carbon-carbon double bond's in resonance, right? So it's conjugated with the aromatic ring. But these hydrogens are more acidic than these hydrogens because they're on the benzylic carbon. So both of those are explanations for why you get this product, or this tri-substituted alkene over this tri-substituted alkene. How about EA1? Whose rule do we need to pay attention to here? Aubry? Markovnikov's rule, right? And what does Markovnikov's rule state? Okay, so when we're doing an addition across a carbon-carbon double bond, the hydrogen goes to the carbon with the most hydrogens. So giving that, what's the answer? Very good. So we could have eliminated right off the bat C. Right? Let's see. B, because that's not Markovnikov, and A, obviously, because that's not Markovnikov either. So D is the only rational answer here. What is the expected product for the reaction shown? There are two up there that you should eliminate right off the bat. B and D. And the reason that we are eliminating B and D? Where did you get the OH, right? You can't get it. That would be like adding water across a double bond. Do we have any water? No, we've got alcohol. So the products we know have to be ethers, right? So it's either going to be A or it's going to be C.
I would say C.
Huh? It's still Markovnikov's rule, right? C is the correct answer. So if we think about this mechanism, so the first step is going to be protonation of the double bond, right? So put the proton there, we get the carbocation there. Why that secondary carbocation as opposed to that secondary carbocation? That's right. Lone pairs, we can draw the resonance structure that stabilizes that. And now the methanol can come in and attack that carbocation and give you that particular product. So see, if you understand the very fundamentals of what the reactions give you in terms of functional groups, you can eliminate almost half of them. I swear to you. You really can. Okay? You can do it. I promise. EA3. As shown in the equation, which set of reagents will convert the alkene into this alcohol as the principal product? What kind of alcohol is it? Is it a Markovnikov alcohol or an anti-Markovnikov alcohol? It is Markovnikov. Very good. You can eliminate because B gives us anti-Markovnikov alcohols. It would, but then followed by OH could displace the bromide, right? But so the answer is? This is the exact example that we used a lot in class. Because remember, if we're using any of the other methods, Markovnikov addition would put the hydrogen here, make a carbocation, which is what kind of secondary, right? And it'll rearrange. You'd get a methyl shift. Anytime you get a secondary carbocation, we do what? We check for rearrangement. We stop and we pause. And we think about it, right? What is the product of the reaction of E1-phenylpropene with peroxybenzoic acid? You can only make A and B? Oh, you can eliminate. Very good. Why can we eliminate A and B? All right, very good. So A and B are eliminated. We know that peroxy acids of any kind will add to a carbon-carbon double bond to make an epoxide. And that's going to give us C or D as possibilities. What's the stereochemistry of our alkene? Trans. So what do we know is going to be the right answer then? D. Remember that this is a concerted reaction. It adds the oxygen atom by forming the two bonds to the carbons at the same time. Right? So whatever the stereochemistry of your alkene starting material is, that stereochemistry will be preserved. And we can see that the aromatic ring and the methyl group here are still trans to one another. Here they are cis. Any questions? What is the major product of the Diels-Alder reaction shown? Eliminate two for me, please. C and D. And why can we eliminate C and D? Well, of course they're incorrect. But why are they incorrect?
C has two double bonds.
Okay.
And C has that weird thing with
All right, that's right. We know that Diels-Alder makes six-membered rings, so C's out of the question because we're getting a 5-4 fused-membered ring. D does give us a six-membered ring, but Grace was absolutely right. We're getting two double bonds, and we know that an alkene as a dienophile and a diene are going to give us a six-membered ring with only one carbon-carbon double bond, right? So it's what?
Those are cis on here, but they're trans.
Why is it B? If you look at it, right, the ester and the methyl group are cis to one another. They are cis to one another in the product. Here they are trans to one another. So remember, your stereochemistry of your alkene in these concerted reactions will be preserved. Okay? How would we get this product? What would we need as our dienophile? We would need a carbon-carbon triple bond between here. Right? Exactly right. We could make that if we had an alkyne. Arrange these ketones in order of decreasing reactivity towards cyanohydrin formation with hydrogen cyanide.
Wait, so like one between those two atoms or that?
Decreasing reactivity would be the
One
most to the least.
two, you get a lot of crap around it. But I don't think two is trans. I think it's going to be.
Cyanide is what? A nucleophile or electrophile? It's a nucleophile, so it wants to attack a more positive, right? And so all of these carbonyls, right, we have to look and see how positive they are. This one has all these fluorines, so it's going to be very electrophilic. So it's going to react very, very quickly. However, here, right, we've got two groups that are really electron donating groups on both of them. So here it's not about electronics so much as it is about sterics. This is a lot more crowded than this one, right? And so the reaction should occur faster there than with 2. And so that's why you see 3 is greater than 1 is greater than 2. Now 3 here. What is the principal product of the acid catalyzed reaction of cyclopentanone with ethylene glycol? It is A. Remember, ethylene glycol plus a ketone or an aldehyde will give, it protects it as what? What's the functional group? No, it's not gem-diol, because gem-diol would be 2 OHs. This is like 2 ethers sharing the same carbon. What do we call that? Acetals and ketals, that's right. So, and is that reaction reversible or not? It is. So ethylene glycol, usually you have to have a little acid catalyst, the ketone. You'll get this if you remove the water. To go back, you just add a bunch of water and you can get back to the ketone, right? What is the product of the sodium borohydride reduction shown? Huh? You tell me, that's the question. Sodium borohydride, is it selective or does it reduce everything? It's selective. It reduces 2 alcohols. Okay. Well, let's find out. Since we know it's a selective reducing agent, which question up there, or which answers can't be correct at all? B can't be correct because that's not a selective reduction. How about C? And why can't C even be right? Well, it reduced this, and then it just took the oxygen off this carbon, right? We never talked about that, did we? And then how about D? D. So the answer has to be? So see, again, process of elimination works pretty good here. But sodium borohydride will reduce aldehydes and ketones. It leaves esters and carboxylic acids alone. Okay? If we wanted to reduce the ester and leave the ketone alone, what would we have to do? We would have to protect the ketone with something like ethylene glycol. Then what would we use to reduce the ester? LAH. And then we would do what to get our ketone back? Put it in some acid with water, right? And we could get our ketone back. Consider the hydrogen atoms attached to 3 different carbon atoms labeled 1, 2, and 3. Rank the attached hydrogen atoms in order of most acidic to least acidic. 2, 1, 3? 2 is the most acidic. Why? Yeah, because it's alpha to 2 carbonyls, right? And so knowing that right off the bat, what can we eliminate? A and C. So that gave us B and D as possible choices, right? And of course 1 here because this is alpha to a carbonyl, and then these, there's no carbonyl alpha to it. So they're going to be very, or not very acidic, right? So they're going to be the least acidic on carbon number 3. Focus on the basics. I kid you not. This exam focuses on the basics like this. You're not going to have to draw a 20-step reaction mechanism or tons of equilibria, okay? There's just no way to do that efficiently on a standardized test. Know your basics. That's what this is after. What would be the major product of this reaction? Before we even look at that, what kind of reaction is this? What's the name of it? It is an aldol, but it's a special name. Do we just call this aldol, or it is a crossed aldol, right? We've got two aldehydes, one that has alpha hydrogens, one that does not. So this is going to be the electrophile. This is going to be the nucleophile. And we know that aldol reactions give what? Beta hydroxyaldehydes or alpha beta unsaturated aldehydes, right? So based on that, what can we eliminate? You can eliminate D. You can eliminate A, because that's not a beta hydroxyaldehyde. And we can eliminate C as an enol. The only answer here is B. So knowing what an aldol reaction gives us, it either gives us an alpha beta unsaturated aldehyde or a beta hydroxyaldehyde. Going through these, I noticed that A, C, and D give me neither of those. So this is, yeah, alpha beta. So this is the alpha beta unsaturated aldehyde. The enolate is generated, right? That attacks the aldehyde, makes the alcohol, but then that rapidly eliminates because of all the conjugation. So got it? You good? Okay. This more or less is as many steps as you'll have on a standardized final. How are we going to approach this problem? One step at a time. You're going to get your scratch piece of paper out and you're going to start working it one step at a time. You're not going to work it in your head.
And that's just one equivalent NaH2, doesn't say excess, correct?
It does not say excess. So, what is NaNH2?
As a reducing agent,
It's a base. It is a base. Now, ammonia and sodium, liquid ammonia and sodium is a reducing agent, okay? But this is a base. So what's it going to abstract? A hydrogen. Which hydrogen will it get? One on the aromatic ring or this one? That one. We know that alkynes are acidic, right? These terminal alkynes, the hydrogens are acidic. About what? About 25 for the pKa. This base has a pKa of around 35. So in the first step, I know that this is going to remove this hydrogen and make an alkanide. Give me a C, triple bond C with a minus charge on this carbon, which is a good what? Nucleophile. So what's going to happen in the second reaction? All right, so it's going to attack here, and what type of reaction? SN2, the leaving group's going to go, and we're going to form a carbon-carbon bond. So now I've got an internal alkyne, right? Now what does hydrogen and Lindlar's catalyst do? It reduces the alkyne to what? An alkene that's cis. That's right. It gives us a cis double bond. A is the correct answer. I know it's not B because that's a pure hydrocarbon, no alkene functional groups. Lindlar's catalyst can't do that. If that was hydrogen and palladium, then it would. But Lindlar's catalyst gives us cis alkenes. What would we put here if we wanted the transalkene? You were thinking about it, and I just mentioned it. H2 and palladium would give me B. You remember the dissolving metal reduction? Liquid ammonia and lithium? That will give you the transalkene. So we can take alkynes, hydrogen and palladium and get alkanes. We can take alkynes, we can take hydrogen and Lindlar's catalyst and get cis alkenes, and we can take alkynes with lithium and ammonia and get transalkenes. What is the product of this reaction sequence? Again, one step at a time, right? So what's going to happen in the first step? We're going to protect the aldehyde as an acetal, right? So we're going to form the ring, and now we've got this alcohol. What happens when we take this primary alcohol and we react it with potassium permanganate? What is it? It gets oxidized to a carboxylic acid, just like Jones reagent would do, right? And so based on that information alone, what can you eliminate? A and B. And then after workup, we get C is the right answer. That's right. See, it's not as hard, right? Huh?
So if we take it as a class, I guarantee you we'll be very high.
It's not a team sport.
We should have little clickers in here we can just discuss and then put it on in.
There you go. Which of the following reactions will produce isopropyl amine? This molecule right here. Eliminate for me. Have we ever talked about adding ammonia across a carbon-carbon double bond? Have we ever talked about taking ketones and converting them to primary amines? Are you sure? We have talked about that, right? We go through an imine and then we can reduce the imine. Okay, so that might be a possibility. Have we ever talked about taking this KCN, and that technically would work, but the problem is what? What would happen with this carbon? We would have an extra carbon. What'd you say?
I was going to say shift, and I said rearrange. Was that wrong?
Yeah, you're not going to get a rearrangement.
I did not say the other word.
Hopefully this microphone didn't pick it up, because it will know, won't it? And how about D? What would happen if we did D? Technically, this would work to give an amine, right? This is the reduction of a primary amide with lithium aluminum hydride. That'll work, but again, too many carbons. So we've eliminated A, we've eliminated C, and we have eliminated D. The only answer that remains is B. And so what happens here is this undergoes imine formation with ammonia, and then the reducing agent reduces the carbon-nitrogen double bond, and you get this. Now, we didn't talk in class about this reducing agent too much for imines. We talked about sodium cyanoborohydride, right? But given the choices that we have here, this is the only one that's practical, the only one that'll come close. These give you too many carbons. This one won't work at all. The only one that remains must be the right answer. You form an imine. So you get that imine, which then gets reduced with the reducing agent to the product. SA6, excuse me. What is this reaction? What's the name? It's the Gabriel synthesis. And the Gabriel synthesis gives us what? Primary amines. So based on that, which two can I eliminate? I can eliminate A for sure, I can eliminate D for sure, and I can eliminate C. Not a primary amine. B is the correct answer. The snowman? What's a snowman? This is a snowman? That's not a snowman.
Got the head with the hat. Well, you make snow angels. Gabriel's an angel, and it works because that's all that matters.
Whatever works for you.